So let us start molecular orbital theory. First of all, why this theory was needed, why it was given. Because we already had valence bond theory, which satisfactorily explained the experimentally observed shapes and geometries of molecules, including coordination compounds as well to some extent. But there were certain other experimental observations which could not be explained by this valence bond theory, like why oxygen O2 molecule is paramagnetic, although it contains total 16 electrons. How we distribute them so that we can get some unpaired electrons to justify its paramagnetic behavior. Similarly, existence of certain species or stability of certain stabilities. For example, He2 plus exists, but He2 does not exist. Something which has positive charge exists, and something which is neutral, its counterpart, that is unstable. And most importantly, behavior of substances which are categorized as conductors, semiconductors, and insulators, that is based on their property of electrical conductivity, this division has been done. What kind of bonding is present in them? Because they also show peculiar behaviors. For example, iron is a very hard, strong substance. So, what kind of bonding it has? Does it has ionic bonding? The answer is obviously no. So, these are some of the other problems which can also be explained by this molecular orbital theory, by application of the molecular orbital theory. Particularly, what are metals or conductors? And you will say that they contain free electrons, which are responsible for its conducting behavior. But we have examples, I mean experimentally observed examples, of the same element which is a conductor in one allotropic form and is not a conductor in the other allotropic form. For example, tin. Tin has two allotropes, gray tin and white tin. Gray tin is non-metallic and white tin is metallic. So we cannot justify a theory by saying that one contains free electrons, other doesn't contain free electrons, because the elements are same, atom is same, and its atomic structure is same in both. So this kind of things can be explained by the application of molecular orbital theory into these type of substances, and then the theory takes the new form called band theory. So that way MO theory is very important. It was given by Hund and Millikan, and I'm sure that some of its basic details you have already read in the 12th class. So I will quickly touch upon them. And here it is said that when two atoms combine or come close together, then there are all the orbitals starting from 1s, 2s, 2p, 1s, 2s, 2p of both the atoms, they combine together. In valence bond theory, we say that only the outermost orbitals are involved in the overlap with the other atoms. So this is a fundamental difference. Now, when the orbitals which should combine together, for example, 1s of this atom, 1s of the other atom, they should contain similar energy and importantly similar symmetry. We have discussed symmetry in detail. I suggest you also to look this kind of to find this kind of symmetry elements in the shapes of various orbitals which you know. Try to find out how many symmetry elements are present in the p orbital. You know its shapes. So that way they should have similar energy and similar symmetry. Then they will combine. And when they will combine, like waves, atomic orbital is a wave function. So there can be two consequences, constructive interference or destructive interference. The one consequence leads to something called bonding molecular orbital and the other leads to anti-bonding molecular orbital. The bonding is lower in energy and higher, and the anti-bonding is higher in energy. On this basis and on the basis of calculations, molecular orbital energy level diagrams have been made, and in the periodic table, if we start from hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, and then oxygen. Then up to nitrogen, and when it starts from oxygen, there is a small difference in the energy level sequence that can be written like this. We will be focusing here only for some simple diatomic molecules and species, and then apply the theory to the band theory. So for up to nitrogen, we have 1s, so sigma 1s, sigma antibonding 1s, sigma 2s, sigma antibonding 2s. And if we take two p orbitals here, there are three in each. So pi 2px, pi 2py, sigma 2pz, pi antibonding 2px, pi antibonding 2py, and sigma antibonding 2pz. Of course, it's 2s. But for oxygen, up to here it is same, sigma 1s, sigma antibonding 1s, sigma 2s, sigma antibonding 2s. But sigma 2pz is lower, and pi 2px, pi 2py, pi antibonding 2px, pi antibonding 2py, and sigma antibonding 2pz. I hope it is recorded. Anyway. So this is the sequence, and the point of difference is here. Now, what is the reason? The reason lies, I repeat, the reason lies in the properties of atomic orbitals. I repeat, atomic orbital, not molecular, of nitrogen atom and oxygen atom. Particularly, the 2s and 2p atomic orbitals of oxygen atom have energy difference of around 1400 kilojoule per mole, while in case of nitrogen, this energy difference is around 400 kilojoule per mole. So what happens in case of nitrogen also, when the two nitrogen atoms combine, initially they make this kind of sequence because it is logical. because it is placing a sigma MO lower to the pi MO, and here it is opposite. So initially this sequence is formed in the nitrogen as well. But since the energy difference in the atomic orbital of 2s and 2p is only 400 kJ per mole, so what happens after the sequence formation? The energies of this orbital and this orbital, in case of nitrogen, becomes very close. And the condition of orbital combination is, I said earlier, they should have similar energy and they should have similar symmetry. Here they tend to have similar energies, but their symmetries are different, so they don't fully combine. They partially combine. And this partial combination leads to the increase in energy of this orbital, this molecular orbital, and lowering in energy of this molecular orbital. So when it increases, it gets placed here above pi level, and this was lower, this further decreases, we don't feel that because of the copy we are writing it below, so it doesn't make much effect on us. So that is the reason why there is difference of energy level diagram sequence. On this basis, you can write the MO diagram for N2 and for O2, and you can calculate the bond orders. I know you can do it, so I won't go into those details. And then you see whether O2 has unpaired electrons or not. When you fill 16 electrons into it, you will find that in the antibonding there are 2 unpaired electrons appearing, which account for or explain its paramagnetic behavior. So it's a question that you write these kind of diagrams for O2, O2 plus 2, O2 plus, O2 minus, O2 minus 2, and compare their relative stabilities based on their respective bond orders. Greater the bond order, greater the stability, and also you comment on their magnetic behavior. When it is O2 plus 2, it means that the 2 electrons we have placed here, they are removed, and so on. Similarly, you can make species for, although N2 is not that practical, but anyway. If you heterodinuclear systems, you can also try, and these are CO, carbon monoxide, Cl. So for CO and Cl, you will use the MO diagram, MO of N type, and for NO and NO plus, NO minus, whatever, you will use the MO of O type. So you write yourself and we will discuss, and then comment whether Cn is more stable or Cn minus. You will yourself find out. The reason you will find out. So these are some of the things you should know in the molecular orbital theory as per your syllabus. Now, let us apply this MO theory to the behavior of conductors, semiconductors, and insulators. And then this theory becomes band theory. Why this term band has been used? Let us start with the simplest metal or conductor like lithium. which has a configuration of 1s2, 2s1, 2p0. One atom has this configuration. And suppose that two lithium atoms are combined. This is one lithium atom, this is another lithium atom, they are combined. Then they will make sigma 1s, sigma anti-bonding 1s, sigma 2s, sigma anti-bonding 2s. The pi 1 will be lower, anti-bonding. So a combination of two lithium atoms produces so many molecular orbitals. Okay. Now, as per this configuration, this will be filled, and this will be like this. This anti-bonding of 2s will remain vacant. So, when two lithium atoms combine in the solid, so many MOs are generated, and electrons can be filled like this. If suppose there are a random number of lithium atoms lying in a lattice, then obviously so many MOs must have been formed throughout the solid, and then when we view so many molecular orbitals like this, then we can see that there are two categories. The lower ones, which are filled with electrons, and the upper ones, which are vacant. So we can see that clearly there are two bands, two varieties. One band is composed of electron-filled orbitals, and the other band is composed of vacant orbitals. So that's what is called bands. And this together has been given one name. This together means the molecular orbitals which are filled. They have been together called valence band, and those which are lying above and are seems to be vacant, they are called conduction. So I will go for a different representation of the bands. I will say that, well, this represents valence band, and this represents conduction band. And here I will make these representations depicting electrons, and here it's vacant, right? Now, the energy gap between these two bands, I repeat, energy gap, it is not physical separation. The energy difference or gap between these two bands is called band gap. And depending on the amount of this band gap, substances have been categorized into three types: conductors, semiconductors, and insulators. If this gap is very low, or you can say that valence band is overlapped with the conduction band almost, then it is called metal or conductor. If the gap is moderate, it is called semiconductor. It's more, it is called insulator. So on your copy, you will make three figures like this and make different separations and show them this is conductor, this is this, based on the band theory. These type of substances are characterized. Now, let us try to understand the mechanism of electrical conduction in this picture. Because in the old theory, you say that there are free electrons, and I told the problems with the old theory. So here, how conduction takes place, electrical conductions. Making arrows like this means that the number of, you see, these are molecular orbitals are kind of waves, electronic waves, and they have momentum, wave momentums. This shows that at one time when there is no external potential on this substance, the number of wave momentum moving along one direction is equal to the number of wave momentum moving along opposite direction. So there is no net current into it. This is the situation. Okay. Suppose that we are discussing an example of a semiconductor, because it is better to make an exemplar. So this is a semiconductor, this is a band gap, this is moderate. Here are some electrons in the valence band, like this. A term also comes here, top of valence band is called Fermi level. Because as you know that some electrons can jump from here to the conduction band in certain situations. So that jumping takes place from on the top levels, energy levels. So that's called Fermi level. So now this is a semiconductor, intrinsic semiconductor. And practically if we apply a potential difference to it at normal temperatures or lower temperatures, it will not conduct electricity. It will not conduct. But on that point I will come later. We will first understand the conduction mechanism, then we will come on the actual condition of conduction. Now, if this is the situation and we applied potential difference across this substance, the positive electrode and negative electrode, you make it a separate figure. You first make this figure and then this positive negative figure, and in this figure the energy of waves, wave momentums, which are pointing towards the positive electrode, they will feel the force of attraction and the energy will be lowered. Here also and here also, although there are no electrons here, but at least orbitals are there vacant, and orbitals are basically negatively charged. There may not be a complete charge of one electron, but it is considered negative. So this situation will take place when you apply the potential difference across it. Okay? Now what will happen? Now obviously within the solid you have created difference. Some energy states which are pointing towards, whose wave momentums are pointing towards the positive electrode, they will get lowered in energy and whereas higher energy. So naturally, electrons should flow from the higher to the lower level, provided what? Provided here there are some vacancies to accept the coming electrons. Here also this can take place. If there are some electrons in the conduction band, they will also come from here to here and the conduction will take place. Right? Suppose this substance is an insulator. The gap is very large here to here and you did the same thing. Then no electrons will flow from this level to this level in the valence band because there are no gaps into it. There are no holes into it. And in conduction band there are no electrons. So the substance will not at all conduct electricity. Okay? But suppose this was a semiconductor and you heat it a little bit, or you do some, you bombard some photons on it, then what will happen? some electrons will jump from the valence band to the conduction band, creating what? Holes in the valence band, and some electrons in the conduction band. Now what will happen when you apply the potential difference? Then the electron can flow from this level to this level because there are holes, and these holes have been created by heating the substance, and that was possible in case of semiconductors because the gap was not very large like those of insulators. It was moderate, so by heating you can easily jump some of the electrons. So the substance could conduct electricity. Obviously, this situation is very much facilitated in case of conductors or metals because there the valence and conduction band is very much mixed. So you don't even need to heat it. If you heat conductors, then at a certain stage you will destroy the lattice itself. You will destroy all the bands and everything, and obviously there will be no conduction. So that extreme is also there. Now if we go to that problem of grey tin and white tin, why one is a conductor, why one is a not, then we have to see their densities. This white tin has more density than the grey tin. I think around 7 point something of white gram per cc of white tin and 5 or less for the grey tin. So the point is that the tin allotrope, which has more density, is conductor. Why this happens? More density means atoms have come close together significantly. So they must have created the molecular orbitals and hence bands. And the gap of energy is also less. But in case of grey tin, the density is less, so atoms are not that close together. So MOs are not properly formed and hence bands are not properly formed. Or may have been formed but gap must have been large. So what we say here the gap is less or here the gap is more also depends on the time, the amount of density of the substance, means how close the atoms have come together to make the molecule. Because when the atom will come together, then only their 1s and 1s will combine, 2s and 2s will combine to make the MOs, and all these MOs together they give rise to binary structures. So that is the reason. Similarly, we can, if we apply pressure to some of the insulators, and if I exaggerate, I can say, to insulators and also to semiconductors, then we can make them better conductors or even full-fledged conductors. Because by applying pressure, you increase the density, you increase the tendency of formation of molecular orbitals and hence bands. So this I talked about the intrinsic semiconductors. Basically your focus is on semiconductors because these are more important materials technologically. We can also explain the behavior of extrinsic semiconductors by band theory. So there are two types of extrinsic semiconductors, N-type and P-type. You already know that how N-type semiconductor can be made. First you take some 14 group element like germanium, carbon, silicon, germanium, tin, lead. You take germanium and you dope a 15 group element into it. Then you call it dope. Doping is a process, material science. Then you get the substance which is an N-type semiconductor. Now what happens? Initially that a 14 group element had this kind of band structure. Here also, initially, and mind you, these N and P type semiconductors don't require to be heated for observing the conduction, unlike in case of the intrinsic semiconductors. So initially, the fourth group element has this kind of band structure, and when you dope a 14 group element with 15 group element, then that impurity, which we call the doped impurity, that will create a new energy level within the band gap of this original host. So what you will dope, that is chosen also by looking at the relative electronegativity and relative sizes. This factor is taken care when we choose something to dope to something. And then a new energy level is created that will contain electrons, because the something which has been doped has more atomic number than the host. So this new energy level is created here, that is called impurity level, and this will contain electrons. So obviously, when there was no doping, this substance could not be a conductor unless it is heated. But now you have doped it, this is the situation, and it will conduct electricity without heating. What we have created? You see, basically there are two things. We need either of the two things for conduction to happen. Either holes in the valence band or electrons in the conduction band, or both. So this new energy level is very close to the conduction band. You can see I have made it very close to the conduction band. This is CB, this is BB. Why it is close to the conduction band? Because it contains electrons, and these electrons won't like to be made here. They would like to be separate from the valence band. Now these electrons can easily jump into the conduction band without any heating or much effort. And that will lead to the conduction. When electric potential is applied, lowering this take place, and this can go from here to here and conduction will take place. Okay? This is the story of N-type semiconductor. In case of P-type semiconductor, we dope a 14 group element with a 13 group element, which has less atomic number. This doping will also create a new energy level, and that level will be vacant, that will not have electrons, like this. So what can happen now? Some electrons from the valence band can go on excursion or tourism to this new level, because in the valence band they are filled. They may see some vacant space where they can go easily, so they can jump automatically without much effort, creating what? Holes in the valence band, which were initially not there until the doping was done. So this was required. Now we have holes in the valence band. Now when you apply the potential difference within the valence band, electrons can go from higher to the lower level and lead to the conduction. So that's what is about the theory of band theory of conductors, semiconductors, and insulators, including the impurity semiconductors. Okay? Rest of the things we'll discuss in the discussion forum.